Thank you so much. It's a great pleasure to be here. Before I get started, is anybody kind of like me in the sense that they kind of grew up thinking maybe nuclear energy was not such a great idea? You know, I mean, raise your hand, it's okay. You know, it's fine, you know, safe place. I did, and I want to kind of confess that at the beginning because I feel like I'm kind of unwinding it after many years. I've now come to think that this is a really, really great thing, and this is something that has incredible potential for our future. In fact, it might be the key to unlocking a pathway to better understanding, better living, better living through science. All kinds of things that, and I had an interaction this afternoon with some students that it's almost kind of left me a little shook is the right word, but we talked a lot about the morality of energy, and there's a lot of things going on in the world right now around energy and around conflict, and we see nations at war with nations, and I can't help but wonder, what would it mean for there to be an energy source that could lead to less conflict, that could lead to greater peace, that could lead to taking away one of the many stupid reasons people fight with each other, you know? I guess, I'm sure we'll figure out new reasons to fight with each other, but, you know, let's see if we could take away a really big one. And I bring all that up because when I first, when I was young, like a lot of the students here, I didn't know anything about nuclear. I wanted to be a rocket guy, you know? I wanted to work in space, and that's how I ended up at NASA doing that. But if I hadn't gone to NASA, I would have never had an opportunity to learn about this technology, to learn about thorium. Now, I have no doubt that most of you are probably going, thorium, what the heck is that? Well, I'll give you the super fast answer. It's something in the Earth. It's the 90th thing on the periodic table. It's all over the place. We got it here in Nevada. We got it everywhere. That's the boring, simple answer. Why should you care? Well, the reason I think you maybe should care is because it might be the answer to solving a lot of these problems, a lot of the things that you might be concerned about in your life. Maybe you're young and you're looking towards the future where you're going to grow up and you're going to get married, you're going to have kids, you're going to wonder how those things are going to turn out for it. Maybe you're near the end of your life and you're wondering about what your legacy is going to be and where things are going to go. Or maybe you're more in the 2/3 place like me, where you're old enough to have seen a lot of stuff happen, but still wondering if there's time to change the course on things. And I've been sobered, forgive me for this intro, but I've been sobered about this by the events of the last couple of weeks and months. A lot of things have happened that caused me to worry about, you know, can we do things that change the hearts of men? In one sense, no. And in another sense, you know, maybe we can improve the situation. So, you know, it is in that spirit, of a time of great conflict and uncertainty that I want to present to you what I've learned and how I learned it a long time ago, and why I keep talking to people about it, and why people talk to me and call me Mr. Thorium, and why I try to run around and tell this story to as many people as I can, because I think it is a story that has to do with you and everybody, and has to do with the future that we're all looking for. You're going to be introduced to a few characters in this story as we go along. A lot of them are good guys. No, maybe a bad guy or two. But all of them have that desire to try to find the answer. One of them in particular is a guy named Glenn Seaborg, who was an eminent chemist at UC Berkeley. Another one is a guy named Alvin Weinberg, who was a reactor physicist, part of the Manhattan Project. You might have heard of Hyman Rickover. He was a famous nuclear engineer who built our nuclear navy. And he had an acolyte named Milton Shaw, who plays a role in this. There are a lot of energy sources out there that we could look at. They're very popular, but some of them have the setback of being diffuse and intermittent, and we need reliable energy. We have got a world full of people who need energy. In addition to our own needs, there's billions and billions of people that currently operate at energy levels far, far, far below what we've got. And those people need to have access to energy in the kind of quantities that we have. We're also concerned about the accumulating amount of carbon dioxide in our atmosphere. Nobody really knows how bad or not bad this is going to be, but it's definitely something to be concerned about and keep our eye on, and we need new energy sources for this. Now, the energies that bind the nucleus, they're really remarkable. They are millions of times greater than the energies that bind the electron to the atom. And there's no in-between between these two levels. I mean, it's an absolute step from one to the other, to go from the energies that bind the electron, which we experience in combustion and digestion and decay and all these other things, to jump to the energies of the nucleus, which are 2 million times greater. Now, in the 1940s, we first learned how to uncover the energies of the nucleus. Unfortunately, we did this in the most negative and horrible way you could imagine, which was nuclear war. We took this discovery and we immediately weaponized it. And we rolled it out to the world, and we scared them to death. I mean, are any of us surprised that we scared the world with nuclear when we introduced it through war? These nuclear materials that make up our world are basic. There's two of them. There's uranium and thorium, and everything else comes from the decay or the fission of this. Now, thorium is about 3 times more common than uranium. But uranium has a real unique feature to it, and that's the fact that it's the only thing that's got nuclear fuel ready to go in it. It has a little sliver of nuclear fuel, uranium-235, and it's only less than 1% of that uranium, but it's the only naturally occurring nuclear fuel on Earth. Now, that guy I told you a little bit about, Glenn Seaborg, he figured out how to turn the rest of these into nuclear fuel as well, but I'm getting a little ahead of my story, and that's it. Okay, I want to introduce you to the best thorium mine in North America, and guess what? It's in Nevada. It's this. They took barrels and barrels and barrels of thorium, and they put it in cargo containers, and they buried it under about 12 feet of ground. So this is material that, if we got serious about thorium, we could just go dust this off and use it for nuclear energy. I really think we ought to do this, by the way, but not a lot of people realize how Nevada is already a part of this thorium story. So what is this thorium story? What are we talking about? Well, we're talking about a way to go and turn thorium into nuclear energy. And I am going to show this video. Okay. Okay. So we're developing thorium nuclear reactors. They have a 2-fluid design, which has got a fuel salt and a blanket salt surrounding them. And these two salts work together to sustain a nuclear chain reaction while maximizing efficiency. This liquid fuel design has many benefits over the solid fuel used in today's reactors. One of the main benefits is it can produce an endless supply of new nuclear fuel via the thorium fuel cycle. So to get a basic idea of how the thorium fuel cycle works, let's begin at the moment of fission. When uranium fissions, it releases energy, but it also releases at least 1 neutron, and that gets absorbed by an atom of thorium. When this happens, the thorium will decay into protactinium in about a half an hour, followed by decay to uranium in about a month. This new thorium will then fission, releasing another neutron that will get absorbed by another atom of thorium, continuing the cycle. The cycle will repeat over and over and over again, thereby creating endless energy from thorium. But to fully understand how this works, we have to dive deeper into the chemistry of the thorium fuel cycle. To do so, we'll begin with the atom of uranium. Uranium's got 92 protons and 141 or 143 neutrons, and when it has this many neutrons, it has a special property. It's fissile. This means it has the ability to undergo nuclear fission. Uranium also will bond to other materials by sharing electrons. And when the uranium gives up its 4 outermost electrons to something else, we can form a compound called uranium tetrafluoride. Now, tetra means 4. And in this case, it's bonded to 4 fluoride ions. This is a very common kind of bonding for fluorine. You probably brushed your teeth this morning with an analogous compound called sodium fluoride. So nothing too crazy here. when a slow neutron will strike an atom of fissile uranium, it sets up a situation that can result in a dramatic fission of the nucleus. Nuclear fission releases a lot of energy, mostly carried by the motion of two products of fission, but additionally, in 2 or 3 neutrons also released. These neutrons have so much energy that they're unlikely to cause another fission until they slow down. We call this slowing down process moderation. And carbon, in the form of graphite, is a very good material to slow down these neutrons. Once they've been slowed down through moderation, neutrons are much more likely to cause additional reactions. For each fission event, we need to make sure at least one of the neutrons keeps the process going. But let's follow the other one. Another neutron needs to find an atom of thorium and be absorbed, setting off a process of change that will transform the thorium into nuclear fuel. Common natural thorium has 90 protons and 142 neutrons, and that gives it an atomic mass of 232, and that's why we call this stuff thorium-232. But when it absorbs another neutron, its neutron count increases to 143, and it becomes thorium-233. But it doesn't stay this way for very long. In about a half an hour, one of its neutrons turns into a proton and releases a high energy electron, and this is called beta decay. Now the nucleus has 91 protons and 142 neutrons, and it isn't thorium anymore. It's another element that's called protactinium. And the fact that it's protactinium now means it is chemically distinct from the molten salt mixture and from thorium, and can be removed. Now, most of this protactinium will decay to fuel, to fissile uranium, but this process takes on average about a month. And while we wait, it's important to keep protactinium away from neutrons. Otherwise, it can absorb some of them and decay into the wrong kind of uranium. So our idea on how to make this separation take place is to use a simple electrolytic cell to remove protactinium from the salt. A very modest voltage will drive the protactinium into a pool of metallic bismuth while extracting thorium from a sacrificial anode. This way we can refuel the blanket with thorium even as we're extracting the protactinium. The fuel salt carrier that's been loaded with protactinium is then transferred into storage. It will remain in storage for several months, giving the protactinium time to decay to uranium. After the decay process is substantially complete, the fuel salt inventory is reintroduced into the reactor, thus refueling the reactor and allowing the entire operation to continue. As you can see, the thorium fuel cycle will continually create new nuclear fuel, thereby creating endless energy from thorium. But this is not possible with thorium alone. Uranium-233 is essential to the process, as the thorium fuel cycle cannot begin without it. Uranium-233 is key to realizing the full potential of thorium and creating an endless supply of energy for the world. So one might wonder, where can we get uranium-233 from? Well, the good news is the United States has pretty much the world's only inventory of uranium-233. The bad news is we don't have a great deal of it, and we are in the process of destroying that which we have. So recently, the president announced that we were going to be able to use plutonium as fuel for nuclear reactors. And I think this is a very, very big deal that has a lot to do with the state of Nevada. What's one of the things Nevada is very, shall we say, infamous for when it comes to nuclear? Yucca Mountain, absolutely. Yucca Mountain has dominated the nuclear story in the state of Nevada. I have never been, don't get mad at me if you're for Yucca Mountain, but I've never been in favor of Yucca Mountain. I've never thought it was a good idea, largely because I thought that there are many useful things in nuclear, what's called nuclear waste, that we could be utilizing. But one of the most important is that plutonium resource. Plutonium is always accumulating in spent nuclear fuel. So if we could use that as a fuel, the opportunity now exists to simultaneously destroy the plutonium permanently, as well as to make new fuel, new uranium-233, to start thorium reactors. And I have a brief animation of this to help explain. All right, so the way it would work is we could consume plutonium in the reactor, and the neutrons would strike thorium and make new uranium-233 fuel that would then be used to start thorium reactors. And you'd only have to do this once to get them started, and then they would be self-sustaining. So as long as you're feeding in more plutonium to get rid of and feeding in thorium for those neutrons to be hit by, you can make more and more and more uranium-233 fuel and start more and more and more reactors. So this is an opportunity that I've been thinking about for a long time, but has only become, shall we say, politically feasible very recently. And I think it has tremendous implications for the state of Nevada because of the issue around nuclear waste. If we can go and take the materials that people have wanted to throw away permanently for many, many years and turn them into something valuable, then maybe they won't try to go and bury them here in Nevada. And we can all move forward much more logically on this issue. That's something I really hope for. So as you can see, like, we've got some of the raw materials that we need, both the thorium and the spent nuclear fuel, to go forward on this strategy. So what else could we do with uranium-233 and thorium? Let me show you something really, really exciting about this. So this is talking about a potential we have to use decay products from uranium-233 to create vital isotopes that are needed to help generate life-saving cancer treatments. Let me just pause this real quick and ask, has anybody here been affected by cancer? All right, no fun, is it? You go to chemotherapy, you get all kinds of treatments, and sometimes you get better, but a lot of times that's not how it goes. Right now, my wife is suffering with colon cancer, and it's spread a lot. And so I was already working on ways that we could use thorium energy to try to fight cancer, but the situation has grown a lot more dire for myself in the last couple of years since her diagnosis. What I want to tell you about here is we made this video before we ever knew about her cancer situation, but what happens a lot of times when cancer metastasizes, it goes to a lot of different places in your body. And I didn't know before her diagnosis like how serious that was. They call it stage 4, when you've gone past wherever the thing was. See, some of you are nodding your head because you know what I'm talking about. And that makes me sad, because I really wish you did know what I was talking about. I'm afraid you do. Once it gets to that point, you're really in serious trouble. Not that you weren't in trouble before, you're in real serious trouble at this point though, because it's hard to get to. So she has metastases in a number of places, and what's taken place is now they're dispersed. They're really hard to get, especially the ones in her lungs. What you want is you want a weapon against cancer. You want something that's going to go and hunt that cancer down and kill them. What does this have to do with thorium reactors? Seems like nothing, right? It does. It connects directly to thorium reactors. And the reason why is because when they were investigating the formation of uranium-233 from thorium, the stuff I showed you about in the early video, they started investigating what happens as uranium-233 decays away. They found out it first decays to thorium-229. There's a gentleman I think in here who was talking to me about a nuclear clock based on thorium-229. Yeah, very exciting work, isn't it? Has the potential to use this isotope to create clocks of extraordinary precision. So what? Why do we need super good clocks? Well, here's one thing, super GPS. GPS that knows where you are within centimeters. Okay, so what? Isn't our GPS good enough? What if you had GPS that could mow your lawn? What if you had GPS that could harvest crops? What if you had GPS that knew what lane of the road you were in and could drive your car? Like, am I crazy? Is that the kind of thing that we might be able to do with nuclear clocks?
You can talk about this later.
Well, at the heart of all GPS is a clock. So if the clock can get better, the potential exists for even more and more hyper-precise location. But then thorium-229 will decay. It decays into actinium-225. And this is a material that they take and they attach to antibodies. And they put it in your body, and it goes and it looks for these cancer cells because the antibody is searching. It has a protein hook on it. And if you have certain kinds of cancers, like prostate cancer, they've already found the hook for this. They know what antibody to attach this to that'll go in there and it'll find it. So there is some really, really exciting work going on right now with prostate cancer using targeted alpha therapy, using those decay products that have come from uranium-233. Why aren't we talking about this more? Well, one of the big reasons is that we hardly have enough of this material. We need more. We have like 0.5 gram of this material in the United States. That's allowing us to even test this on just a few patients a week. We need a lot more material. How do you get more material? There's a lot of ways, but one of the best ways to get it is to create thorium reactors that have uranium-233 in them, and then some of that will decay to thorium-229, which you can then harvest, and you can then make special cancer-fighting medicines from this material. I was excited about this before my own situation happened, but now I'm like 100 times more excited about it because I really, really, really want to help not only my loved ones, but all the other people. Until you get in it, you don't really have any idea how much people are suffering. And then you find out, and then you get pretty sad. But with this, there is the potential to go and treat cancers in a way that would be completely different than the way we treat them today. We use chemotherapy. We're basically kind of poisoning people. This would have the potential to go in and kill your cancer cell by cell. As long as you had that hook, that antibody that knew what it was looking for. You can basically bring a mini nuclear bomb to the cell. The great thing about it is no cancer cell can survive a strike from that kind of radiation. It's too intense. Some of you know about alpha radiation are nodding your heads going, yep, that'll do the trick, you know. But it's extraordinarily precise. So imagine a future where we could have a cancer-fighting modality where you don't have to go in and have chemotherapy, you don't have to get nauseous, you don't have to get sick, your hair doesn't have to fall out. Trust me, you don't want any of these things. Imagine a future where you get told you got stage 4 cancer and the doctor says, well, don't worry, we're going to get you in next week and we're going to prepare a dose of alpha therapy for you, and then a few weeks later we'll give you another dose, and a few weeks after that we'll give you another dose, and then you're going to be all better after that. I mean, that sounds like a miracle, doesn't it? It sounds like a dream. I mean, I almost want to cry thinking about how great that future would be. But you know what? That's the future that happened for all of us when antibiotics were discovered. Antibiotics transformed a world of death into opportunities for life. Imagine a future where fighting cancer is about as scary as taking your antibiotics. At that point, you might look back and think, well, gall, would you rather be the richest person in the world in 2025 or a regular dude in 2075? You'd probably say, well, I'd rather be a regular dude in 2075 because we got a cure for cancer in 2075. You could die of cancer in 2025. You know, that's what I'm hoping for. And that's what this is all about, this idea of connecting a radionuclide to an antibody so that it can then be injected into the patient and go seek out and find these cancer cells, binding to them. And then when the radionuclide decays, it shoots that alpha particle through the cell. It kills the cell with extreme prejudice because the power of that alpha is thousands of times greater than a beta particle, which is basically just an electron. I used to have brothers, and it's like the difference getting shot by a BB. Anybody been shot by a BB gun? Yeah. All right. You been shot by a shotgun? Yeah, you wouldn't be here if that happened. So one of these you live through and the other one you don't. So with this alpha therapy, you can go and find these cancer cells and destroy them cell by cell. Whereas with other kinds of radiation, like beta radiation or gamma radiation, the area of attack is so much greater. Alpha radiation, we're killing within about 1 to 3 cells of an alpha particle, and with beta radiation, we're killing, you know, within hundreds of cells. So it's just a completely different level of precision. Again, sounds great. You know, why isn't everybody doing this? Well, it's just we don't have a lot of access to these alpha-emitting radioisotopes. They're very rare, and nature doesn't exactly give us a ton of choices on this. And the most promising alpha-emitting radioisotopes are coming from the thorium fuel cycle. They're coming from the decay of uranium-233. So being able to build thorium reactors, being able to destroy our nuclear waste, could be the pathway to generating medicines that are going to enable us to have a far better chance of curing cancer. Or curing cancers, at least cancers, if we can target it, if we can go after it, we're going to be able to kill it. And that's a future really worth hoping for. So there's the chance that at this stage in the presentation, I hope you don't mind, I'm going to take a little drink here. You might be wondering, you know, why didn't this happen? If you're telling me these things, Kirk, there's got to be a catch. Why didn't this take place? And if you're thinking that, I don't mind you. I don't blame you for thinking that. I thought the same thing for the longest time. In fact, I wrote my master's thesis at the University of Tennessee on the history of thorium, starting in the Manhattan Project. I wanted to get to the bottom of what went wrong. Why didn't we have these things? You know, what took place a long time ago? Because when I found out that people like Glenn Seaborg and others had devised this, I really wanted to understand what had gone awry. The really short version of the story is wasn't any good for bombs. But let me give you the slightly longer version. Okay. So this video is going to talk a little bit about some of that pioneering research that was done in nuclear energy and why the thorium reactor that we're talking about didn't take place. It actually has to do with a weird variant of uranium called uranium-232. And let me talk with you just a little bit about how this was realized and what the implications were for the development of nuclear. So we start with this guy, Glenn Seaborg. I mentioned to him, he's from UC Berkeley. He's one of the important pioneers of nuclear chemistry. And he discovered a ton of elements using this device called a cyclotron. He used neutrons from the cyclotron to transform natural uranium into tiny amounts of a new element he called plutonium. You might have heard of this stuff. But that wasn't the only thing he did with this machine. He also bombarded thorium with a neutron to get protactinium. He was the first person to discover uranium-233 from thorium. Now, plutonium was chemically distinct from uranium, so he could use chemical processes to get these two apart from one another. And that was a very big deal. He could also do the same thing with thorium, protactinium, and uranium. But at the same time these discoveries were being made, the United States had been attacked and World War II had begun. And they didn't want nuclear energy for power generation, they wanted nuclear energy for weapons. So they engaged Seaborg in this process, and he joined the Manhattan Project, and making plutonium became his greatest priority. Now, Seaborg also wondered if uranium-233 could be used in nuclear weapons. And the next year, he was able to make larger amounts of plutonium and uranium-233 using one of the very first nuclear reactors here at Oak Ridge. He discovered, as we've explained, that uranium-233 was very special. As it was consumed in fission, it released enough energy to replace itself from abundant thorium. And that meant that thorium could be an almost unlimited source of energy. But he also discovered, in the process of working on this, that this uranium was always contaminated with another isotope of uranium called uranium-232. It's one mass unit lighter than uranium-233, but it's thousands of times more radioactive. It decays into isotopes of lead and bismuth that emit penetrating gamma radiations. And Seaborg knew that heavy shielding would be required to prevent gamma radiation from damaging electronics and materials in any nuclear weapon they might build. This meant that weapons made from plutonium or uranium-235 would be lighter, simpler, and far more practical than weapons made from uranium-233. And this is because plutonium and uranium-235 decay from alpha emission and are easily shielded by as little as a piece of paper. In addition, uranium-232 and uranium-233 are the same element, so they're virtually impossible to separate from one another. This meant that uranium-233 would be permanently contaminated with uranium-232. So once this was realized, Seaborg recommended to General Leslie Groves, who at that time was the director of the Manhattan Project, that they stop considering the use of uranium-233 in weapons. Ultimately, plutonium was used in the first successful test of a nuclear weapon at Trinity, and a few weeks later again at Nagasaki in Japan. After the war, the government plowed enormous resources into producing highly enriched uranium and plutonium for more weapons. Unfortunately, nuclear fission had been introduced to the public in the most horrible way. But the government also tried to tell the public that atoms could be used for peace. Soon they felt public pressure to show how nuclear fission could power cities instead of destroying them. Scientists and engineers considered concepts for both solid and liquid nuclear fuels. The potential of thorium in a reactor was compelling. Scientists like Alvin Weinberg and Eugene Wigner believed in and advocated for thorium reactors. These reactors would transform common thorium into a nuclear fuel by way of the thorium fuel cycle, allowing them to continually run on thorium alone. However, as I mentioned, they did need another fuel for the initial startup. Using uranium-233 as the starting fuel was a potential option, but making solid fuels from uranium-233 was challenging and expensive because of that penetrating radiation from U-232 decay. This would require a tremendous amount of shielding and protection during the entire fabrication process. It was actually much easier to make solid fuels from uranium-235 instead because it had almost no radioactivity. So when they began to build a reactor in 1955 in New York, they chose uranium-235 in the form of highly enriched uranium as the starter fuel. By not using uranium-233, they avoided the challenge of gamma radiation from uranium-232 decay, at least initially. But operation of the reactor created U-232 contamination so significant that the spent fuel could not be chemically processed for reuse, creating excessive nuclear waste. At Oak Ridge National Laboratory, liquid-fueled thorium reactors based on fluoride molten salt showed more promise. Thorium and uranium would be dissolved into the liquid fuel, which could be used and processed directly. This avoided the problem of fuel fabrication completely, and molten salts were impervious to damage from gamma radiation. Thus, the first nuclear reactor to operate on uranium-233 fuel was a molten salt reactor at Oak Ridge in 1968. But around the same time, Admiral Rickover, who oversaw the building of the first civilian reactor in 1957 in Pennsylvania, was now imagining how they could build a thorium reactor. They wanted to test whether a thorium breeder reactor was possible. And since the breeder reactor required uranium-233 at startup, they had to tackle the challenge of U-232 contamination. They knew there were three main ways it can form in the nuclear reactor. The first way is when uranium-233 is struck by a fast neutron rather than a slow neutron. When uranium-233 is hit by a neutron that's been slowed down through moderation, it's much more likely to cause a fission. But sometimes the neutron hasn't slowed down enough through moderation, and we call these kind of neutrons fast neutrons. And while they're unlikely to cause reactions, sometimes they do. When a fast neutron strikes uranium-233, it sometimes, instead of causing a fission reaction, it actually knocks a neutron off, and this forms uranium-232. Another way uranium-232 can form is when a fast neutron strikes thorium-232, also knocking off a neutron and forming thorium-231. And that decays to protactinium-231 in about a day. But protactinium-231 decays very slowly and has a huge appetite for absorbing neutrons. And when it happens to absorb that neutron, it becomes protactinium-232, which decays to uranium-232. Finally, the third way that uranium-232 can form comes from thorium itself. When thorium is mined, it contains trace amounts of thorium-230, which comes from the decay of natural uranium-234. The amount of thorium-230 present in the thorium depends on how much uranium it was around when it got extracted. Thorium-230 also has a huge appetite for absorbing neutrons, and when it does, it forms thorium-231. And that then follows that same pathway of formation that I mentioned earlier, leading to the formation of uranium-232. So these three pathways all led to this problem, and Rickover knew that he was going to have to solve this in order to go forward. In order to do so, he selected thorium ores that were isolated from uranium, and then he went and he took these special thorium ores and he loaded them in the periphery of a special production reactor. And that avoided all of those fast neutron effects I mentioned by giving plenty of room for the neutrons to slow down. So this reactor successfully created uranium-233 from thorium with very little contamination. And Rickover was able to start his experiment in December 1977 with a command from the White House by President Jimmy Carter. This reactor successfully generated millions of megawatt hours of electricity for consumers in Pennsylvania, all from thorium. And in the end, there was more uranium-233 in the reactor when it was shut down in 1982 than when it was started. It remains the only thorium breeder reactor that is operated to date. However, the technique they used to limit uranium-232 contamination only applied to the first batch of fuel. Inside the reactor, all of the fuel had been exposed to fast neutrons, which led to the formation of significant amounts of uranium-232. And the ceramic fuel that they had used was very difficult to chemically process, almost impossible. So it was disposed of as waste rather than recycled as fuel into a new nuclear reactor. Despite Rickover's success with the thorium reactor, it was really Weinberg's molten salt reactor that had the most promise for using thorium efficiently. Even though it had not been demonstrated, it would be much easier to chemically process molten salt fuels. This would allow for the removal of fission products that are created when uranium fissions. And these fission products contaminate the fuel, but molten salts allow for their removal and repurposing, drastically reducing waste. This is not possible with solid fuels in the reactor. Liquid fluoride would allow for fresh thorium to be continually added to maintain the thorium fuel cycle, creating an endless supply of energy from thorium. But by the 1980s, government support for both molten salt reactors and the light water breeder reactor approach had completely dried up. Funding went almost exclusively to fast reactors that bred plutonium, plutonium that would be suitable for nuclear weapons. Our company was formed because we recognized the potential of liquid fluoride reactors to implement the thorium fuel cycle. And since our reactors don't use solid fuel, they are immune to the challenges posed by the buildup of uranium-232. This is one of the many reasons why we think liquid fluoride reactors and the thorium fuel cycle go hand in hand with one another to move us towards a future of energy abundance. Now, during my opportunities here today, I was very lucky to, I was very lucky to talk to some of the researchers, and they are looking at chemical processes, electrochemical techniques, all kinds of ways to implement what I just talked about in this presentation, to go and add fuel in and to take fission products out. And this is very exciting to me because I didn't know that some of this work was already going on here at the university. But this is the kind of thing that could make this thorium future possible. Now, I mentioned in this video that many of these materials were taken and thrown away as waste. Anybody want to hazard a guess where they got thrown away? Yeah, that's right. They're all here now, and they're mixed up in ways that are not useful anymore and will pose a radiological waste hazard for over 1 million years. This is not good. And unfortunately, more is coming if the government continues on the path that it's on. So we are trying to go and explain to them the value of the thorium fuel cycle so that valuable materials, including thorium and uranium-233, can be preserved. Preserved to make power, preserved to make medical isotopes, preserved to make nuclear clocks, techniques that will allow us to go and destroy nuclear waste so we don't have to build a repository like we've talked about, and allow us to keep bad things out of the state of Nevada and bring good things to the state of Nevada. So let me conclude with a very brief kind of view of where we think we're going with this. This is what we think a small modular FLIBE reactor in the future is going to look like. And it's a very compact facility because the reactor can operate at low pressures but at high thermal efficiency and can potentially avoid using water entirely. So we can go and put these reactors in places where water supplies are strained. We can make electricity using these reactors at much higher efficiency than what we've been talking about. And there we go. And we can locate them near loads like a mine, a data center, a remote locality, all kinds of places where typical nuclear technology has not been able to reach. Up to this point, the state of Nevada hasn't had any nuclear power sources, at least to the best of my knowledge. So this could be an approach that could unlock a nuclear future for this state And I also think it could unlock a nuclear future where the state can show great leadership in implementing a form of nuclear energy that shows the rest of the nation that nuclear energy does not have to be based around waste or weapons or danger or uncertainty. And this is my hope and my vision, and to the degree that I've been able to explain these things, I appreciate it. Thank you very much, and I'm happy to take questions.